Welcome back to Chemical Reactor Design. We are now in lecture 13. As you know, chapter 3, which discusses rate laws and stoichiometry, is divided into two parts. The first part was rate laws, where we learned how to write rate laws for different reactions, and part 2 is the stoichiometry, where we're going to learn about stoichiometry. Now that we have shown how to write the rate law as a function of concentration, we need only to express concentration as a function of conversion in order to size reactors. If rate law depends on more than one species, for instance, rate law depends on concentration of A, B, C, and D, we must relate the concentrations of the different species to each other. This relationship is easily established with the aid of a stoichiometric table. You all know that the number of moles of A is related to number of moles of B and C and D through what's known as stoichiometry, or the stoichiometric equation. So hence we're going to establish what's known as stoichiometric table. In formulating our stoichiometric table by using conversion, we shall take species A as our basis of calculation to put everything on a basis of per mole of A. Therefore, the stoichiometric equation has to be rewritten such a way that we will have number 1 here, 1 mole in front of A. Also recall that the symbol delta, or the total stoichiometric number, which you have seen in thermodynamics, so delta, the total stoichiometric number, represents the change in the total number of moles per mole of A reacted. So basically you want to know how many, or the solution, how the number of moles in that solution have changed with every 1 mole of A reacted. So obviously you can calculate it through this equation. You calculate the change in the total number of moles and you divide it by the change in number of moles of A, which is your basis of calculation. Or if you had a flow system, then instead of N you use F, so it will be the change in the total number of the moles flowing divided by the total change in number of moles of A, molar flow rate of A, of course. And it can be calculated simply from summing all the stoichiometric numbers. Okay, so we said delta, the total stoichiometric number, is the change in the total number of moles per mole of A reacted, and we gave these equations. And we said also it can be calculated, delta can be calculated from the summation of all the stoichiometric numbers. So I'll leave you with this exercise to do it at home. Go ahead for this reaction where A produces 2 moles of B. Calculate delta from this equation and then calculate it from this equation. Okay, let's talk about batch systems now. What are batch systems or batch reactors used for? Of course, it's used for the production of specialty chemicals where you don't need to produce a lot, and also use it in the lab to obtain kinetic data. For instance, you find the rate law, what's minus R8 function of, and the value of K, and the order of reaction, and so on. Okay, so species A is our basis of calculation. The number of moles of A initially present is symbolically written as in A0. Exactly. Moles of A consumed. How do you evaluate moles of A consumed? Basically, you have an A0 minus NA. And then remaining moles of A, of course, it's NA. So in similar fashion, we construct the stoichiometric table to determine in B, in C, and in D. So let's do this together. Again, this is our reaction, and this is the stoichiometric table. We start with the species A, B, C, D, and we have some inerts as well. Then we find the initial number of moles. So here we go. For A, we have an A naught. For B, it's an B naught, and so on. The change. Then we talk about the change. Obviously, the change is what you final minus initial, correct? So finally, we had NA, right? At time final, we have NA. And initially, we have NA naught. So when you subtract NA from NA naught, okay, this is simply reminds you with the definition of X. Remember what X was defined as? Yes, so X was simply defined as NA naught, right? Excuse my writing skills, minus NA, and this is basically divided by NA naught, correct? It's not easy to write using the mouse. Okay, so if we wanted NA minus NA naught, so simply it will be minus NA naught times X, which is shown here. Okay, then let's find the change in number of moles of B. We can do also NB minus NB naught. However, there's an easier way, which is using the stoichiometry. So if this is the change in number of moles of A, then the change in number of moles would be the same quantity multiplied by B over A. If you don't remember, just use unit conversion. The same thing would be for C. However, you will have a positive sign because now you are producing C, and so it's C over A times NA naught times X, and the same thing goes with D. Do you have any change in number of moles for the inert? Obviously not. Okay, so what's remaining? What's remaining is NA, right? It's NA, and you can calculate what's remaining from taking the initial value, here we go, and add to it the change. If you take the initial value and add to it the change, this will give you what's remaining. So let's do the same thing for all the other species. So what's there initially and add to it the change. So here we go. And what about the inert? Obviously it will be the same. So Ni basically equals Ni naught. Okay, let's sum up all these quantities to find Nt, the total number of moles. So let's do that. When we sum up the first term, obviously you will get Nt naught. And when we sum up the second term, we find that we have a common factor, which is Na naught times X. Okay, so we'll take it as a common factor. So what's remaining? What remaining is minus 1 minus B over A plus C over A plus D over A. If you sum them all, you'll get the total stoichiometric number, which is the delta. Okay, so let's write a general equation for Ni as a function of X. So let's see that. If you want to write the general mole for Ni as a function of X, which is the remaining number of moles of a species I, then simply it will be Ni equals, see, it will be Ni naught, and then you have, of course, Na naught times X. There we go. And what are these numbers? Minus 1 minus B over A plus C over A. Obviously, they are the stoichiometric number, So this is a general equation which I can use to write Ni, the number of moles of I, or the remaining number of moles of I. Okay, Na may be taken as a common factor. So let's take Na naught as a common factor. If we take Na naught as a common factor, so you'll have here Ni naught divided by Na naught plus nu I, the stoichiometric number, times conversion. It is found that this ratio is very useful. So basically it tells you, look at the feed and compare all the other species to the compare the number of moles of all other species to the number of moles of your limiting reactant. So it's a very useful term. Therefore, we can define it as theta I. So let's rewrite the above equation now. So it becomes Ni equals Na naught, and this guy is theta I plus nu I times x. Now we have a general equation where we can express Ni as a function of x. Ni as a function of x. Okay, and don't forget what theta is. Theta I is Ni naught divided by Na naught. If you multiply both the numerator and the denominator, if you divide both the numerator and the denominator by V naught, then you will get the concentration. So you can write it as a function of concentration as well. Ci naught divided by Ca naught. Or you can also use the mole fraction. Yi naught divided by Ya naught. So this is the definition of theta I. Okay, recall that the kinetic rate law, for example, minus Ra equals K times Ca, is a function of solely the intensive properties of the reacting systems. For example, temperature, pressure, concentration, and if you're using catalyst as well. Okay, so recall that minus Ra depends on Ci rather than Ni. So yes, I know we have developed an equation for Ni, but in fact, if we want to write the rate law, then the concentration Ci becomes more handy than, or handier than, Ni itself. So how do we convert Ni to Ci? Very simple, right? Okay. There we go. This is how you convert Ni to Ci by dividing it by the volume. So the concentration of species I is the number of moles of I per unit volume. In general, Cix can be written as, so if you want to express the concentration as a function of x, basically you should find Ni as a function of x and divide it by the volume, which also could be function of x. So we are saying the number of moles of species I changes as the reaction progresses, as x changes. Likewise, the volume of the reaction mixture could change due to the change in few things. But anyway, it does change as the reaction progresses. We know how to write Ni as a function of x, correct? We have just developed this, right? So now we need to learn how to find V as a function of x to obtain Ci as a function of x. So again, we learned how to write this. Now we need to learn how to write this in order for us to be able to write concentration as a function of x. Let's start with constant volume batch reaction systems. Constant volume batch reaction systems. So we are saying that the volume of the reaction mixture is fixed. So some significant amplifications in the reactor design equations are possible when the reacting system undergoes no change in volume as the reaction progresses. These systems are called constant volume. Obviously, the volume is constant. The volume of the reaction mixture in this batch reaction system, the volume is constant. So we call it constant volume, or it's also called constant density because of the invariance of either volume or density during the reaction progress. Okay, I need to remind you of something. Remember what density is a function of? Density equals mass, correct, divided by volume. So let's look at the density of the reaction mixture. The density of the reaction mixture equals the mass of the reaction mixture divided by volume. If the system is a constant volume system, so this guy is constant, V is constant, and then let's ask ourselves, what about the mass? What about the mass of the reaction mixture? Does it change? Does the mass of the reaction mixture change as the reaction progresses? Of course not, because mass is conserved, right? It's not created nor destroyed, so the mass remains constant. So we have the volume is constant, the mass is constant, therefore the density is constant as well. This situation where the volume, which we are looking for, and we want to see how it changes as the reaction progresses, yani how it changes as x increases. So in this situation, in fact, the volume is not function of x. In fact, the volume equals the initial volume because the volume does not change as the reaction progresses. So this situation may arise from several cases. The first case, if you have a sealed constant volume vessel, so the vessel has a constant volume, so no matter how far the reaction goes, the volume remains constant. Then we have the liquid phase reaction. You know that liquids are weak function of temperature and pressure. So even if the temperature or the pressure is changing as the reaction is progressing, then the total volume does not change much because the volume for liquid is weak function of temperature and very weak function of pressure, unlike, of course, the gas system, the gas phase reactions. Okay, not to mention that whenever we use liquid phase reactions, we actually have lots of solvents. So as the reaction progresses, the solvent actually is not changing, it's the same solvent, so you get the volume constant. Actually, the density of the reaction mixture is almost equal to the density of the solvent, which does not change as the reaction progresses. And the last case is where you have no change in the total number of moles during isothermal and isobaric gas phase reaction. So that's the last situation where actually the volume does not change. Let's look at that. V equals N, right? And T, of course, we're looking at the total number of moles, and then R times T divided by P. So if the total number of moles in T is not changing as the reaction progresses, for example, you have 1 mole of A gives you 1 mole of B. So as the reaction progresses, the total number of moles does not change. R is constant, T is constant because you're operating isothermally, and P is constant because you're operating isobarically. Therefore, if in this case nothing changes here, therefore the volume of the reaction mixture does not change even though it's a gas phase reaction. Okay, so let's take an example. For the constant volume reaction system, write the rate law for the reaction A plus 2B gives you C in terms of X. The reactants are charged at a stoichiometric ratio and the reaction follows an elementary rate law. Okay, so we want the rate of reaction, okay, the rate law as a function of X. So the first thing to do is to write the rate law. We know that the reaction follows an elementary rate law. Therefore, the rate law can be written as minus RA equals KA CA to the power 1 times CB to the power 2. In fact, this rate law is elementary. Okay, so it follows a power law model where you have here the power. Okay, the power here is identical to the stoichiometry here, as you can see, because the reaction follows an elementary rate law. Okay, then how can we introduce X to the right hand side? You got it right. So we need to find the concentration as a function of X. Concentration of A as a function of X, then we find the concentration of B as a function of X and substitute in this equation, then you will have minus RA as a function of X. So start with CA. Okay, we know that CA equals NA divided by V, correct? And we know how to write NA as a function of X. So NA equals NA naught times 1 minus X. What about V? V simply equals V naught because we have a constant volume reaction system. And then upon simplification, we have here NA naught divided by V naught gives you CA naught times 1 minus X. Let's look what we have for B. CB. CB equals NB divided by V. Okay, how do you write NB as a function of X? We have all learned that NI, correct, equals NA naught times theta I plus nu I times X. So let's write Ni for B. So we have NB equals NA naught times theta B plus nu B times X. What about V? Again, V equals V naught. Okay, now we need to find the value of theta B. Theta B. So whenever we talk about theta, actually we have to look at the feed. We don't look at the stoichiometry. No, we look at the feed because as you remember, theta I equals N I naught divided by N A naught, correct? So we're always looking at the feed. See the not here, the not here, so we're looking at the feed. So for B, it will be NB naught over NA naught. So let's look at the feed. Let's see. The reactants are charged at stoichiometric ratio. See, the reactants are charged at stoichiometric ratio. So we go to the stoichiometric ratio and we know that for every 1 mole of A, you have 2 moles of B. So theta basically equals 2 divided by 1, which is 2. Okay, let's look at nu B. In order to look at nu B, which is the stoichiometric number, we need to look at the stoichiometric equation. But before we do this, let's make sure that the stoichiometric equation is written in such a way that you have 1 in front of the limiting reactant, which can be assumed to be A here. Okay, so it's written correctly. So what is the stoichiometric number for B? It is simply minus 2 because B is reactant, correct? Okay, so here we go. Theta is 2, nu B is minus 2, and NA naught is written as well. So let's see, we can take 2 as a common factor. So we have here 2, and then we have 1 minus X, and of course NA naught divided by V naught is simply CA naught. So now that we have CA as a function of X, CB as a function of X, now we can go back to the rate law and substitute for CA and CB with their respective equation, and don't forget to use the power 2 here, and upon manipulation you'll get the rate law. So now the rate law is written as a function of X. Okay, let's have another example. Let's look at this example. For the constant volume reaction system discussed earlier, A plus 2B gives you C. Calculate the concentrations of the involved species when X equals 0.8 if the initial mixture consists of A at a concentration of 10 mole per liter and B at a concentration of 25 mole per liter. So you're thinking that this is very similar to the previous example. Yes, it is very similar, except that now we want to write concentration as a function of, we find the value of the concentration at this given conversion. Therefore, we need to find again C as a function of x, CV as a function of x, and CC as a function of x as well. Okay, so what's the difference then? The difference that the feed is not introduced at a stoichiometric ratio. However, there is another specification given for the initial mixture, for the feed mixture, and it's specified that Ca naught is 10 mole per liter and Cb naught is 25 mole per liter. So let's discuss a couple of hints and then I'll leave you to do this example at home. So the first hint, you should ask yourself which species is the limiting reactant, because based on the answer to this question you might need to rewrite the stoichiometric equation in a different way, where you have one in front of the limiting reactant. Okay, that's one thing to think about. The other thing to think about is the value of theta b. So we learned that theta b equals nb naught over Na naught, or it can also be Cb naught over Ca naught, correct? And in this case, here you have 25 divided by 10, which equals 2.5. And the earlier example, theta b was 2. And again, Shabab, as I said, whenever you see a theta, you should look at the feed. You should look at the feed. You shouldn't look at the stoichiometric equation. However, when you need to find the value of nu b, that's when you look at the stoichiometric equation, and in this case it is minus 2. Okay, so we learned how to write concentration as a function of x, and we also learned how to substitute that in a rate law to find the rate of reaction as a function of x. And all of that was for a batch system. Now we're going to talk about flow systems. Flow systems. So construct a stoichiometric table for a flow reactive system. Okay, it's not much difference, except that instead of using Ni naught, we'll use Fi naught, and instead of using Ni, we'll use Fi. Everything else is exactly the same, as you can see here. Okay, and recall that for this case, for a flow system, theta b equals Fb naught over Fa naught, because it's a flow system. And again, it can be expressed as a concentration ratio or mole fraction ratio. In general form, the molar flow rate of a species I is, again, Fi equals Fa naught times theta I plus nu I times x. Just similar to the previous equation we developed, where you had Ni equals Na naught times theta I plus nu I x. How do you find Ft from the above equation? Obviously, you need to sum both terms, right? The left hand side and the right hand side, because summation of the left hand side will give you Ft, and summation of right hand side will give you this. Okay, you can do this at home as well. Equations for concentrations in flow systems. Okay, let's learn how to convert Fa to Ca for a flow system. Yes, correct. So if you want to convert Fa to Ca, you have to divide it by epsilon, the molar flow rate. So Fa divided by epsilon gives you simply Ca. In general, Ci is a function of x. can be written from Fi as a function of x divided by epsilon, the volumetric flow rate, as a function of x. The general equation can therefore be written as this, because we know how to write Fi as a function of x, correct? Now, obviously, we need to learn how to write epsilon as a function of x in order to get Ci as a function of x. And this is something we're going to learn in the following lectures.